Hello, 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 hello. What's up? I hope that you're all doing very, very well and are excited about today's class. I know I am. It's a beautiful Sunday outside, beautiful weather. And what we're going to do is we're going to derive three equations of what? Uniformly accelerated motion in one dimension, which are these three equations. I bet you have seen these equations before. Everybody has. We're going to derive these equations from the first principles, from the very, very basic equations. I'm your personal physics tutor, Dr. Rima McMullen. Let's start our class now. Before we begin to derive these three equations, let's see how many different variables are involved. So we have this v over here. What is this v for? It is for final velocity. Very well. V naught. V naught is for what? Initial velocity. All right. Next we have A, which is acceleration. And in this case, it is going to be uniform acceleration. Next we have delta x. Delta x is nothing but x minus x naught. So this x naught is the initial position and x is the final position. So x minus x naught, it is displacement. It is displacement that is made in time t. And x naught, like I said, it is initial position, and x, it is our final position. Now, you will also notice that v naught, it is in all the three equations. So v naught is in all the equations, in all three equations. What else do we have in every single equation? Is there anything? Sure is. Acceleration. Acceleration is also in all the three equations. And time t is in the top two equations. This is in two equations. All right. And then we have v, which is final velocity. It is in two equations. And we have delta x, that's in two equations as well. Now, next what we're going to do is we're going to see what are the different ways to derive these equations. Yep, there's more than one way. The first method is the algebraic method. And the second method uses calculus. The third method is the graphical method. So what we're going to do is, first thing we're going to do is derive all these three equations using algebra. Here's our equation number 1 that we want to derive algebraically from the first principles, from the most basic equations. Now, which basic equation, which fundamental equation relates the variables v, v naught, a, and t? And it turns out that the average acceleration, it is defined as v minus v naught divided by t. Okay, so you see that this equation for average acceleration, it has all the four variables that we are seeking in equation number 1. Could you rearrange equation for acceleration to get equation number 1? Sure can. How? In equation 1, we have a and t together, while in this equation for acceleration, we have a by itself on the left-hand side. What if I multiply both sides of this equation for acceleration by time t? When I do so, I get a and t together. Let's write that down. We get a times t equals what? V minus v naught divided by t times t. So what does this give us? This gives us at on the left hand side, And on the right hand side, the t's cancel out. What are we left with? V minus V naught. Now you can see that this equation is already starting to look kind of like equation number 1. All you have to do is add V naught to both sides of this equation. And when you do so, what do you get? You get V alone by itself on the right hand side, and the left hand side it becomes V naught plus AT. Now compare this equation with equation 1. All you have to do is what? Swap left and right hand side of this equation that we just got. Call it equation uppercase A. Swap left and right. What do you get? You get equation number 1. So here's your equation number 1 obtained how? Obtained algebraically. I'll write this down. Go ahead and swap left and right and you get your equation number 1 derived. What's our equation number 2? Equation number 2, let's write this down. That says delta x equals V naught t plus 1/2 AT squared. Okay. Now, the average velocity to go from initial position x naught to the final position x, that is in order to make displacement equal to delta x is what? V bar, the average velocity equals displacement x minus x naught divided by t. But this is not it. This is not the only way to write down average velocity. In this special case, what special case? What? One-dimensional uniform acceleration. In this case, uniform acceleration means acceleration is constant. And acceleration is equal to the slope of what? Velocity time graph. So if the slope of this velocity time graph is constant, that means velocity has to be what? It has to be a linear function. It has to be a straight line. It could be whichever way. It could be going up. It could be coming down. It could be flat. But it's going to be a line. And in this diagram here, this is V naught, initial velocity. Here's your final velocity. Given this initial value of velocity V naught and the final value of velocity V, what is the value of the average velocity V bar in terms of V and V naught? That is going to be what? That is going to be V bar equals V naught plus V divided by 2. Now here we have two equations, both for V bar. Can we equate the right-hand sides of these two equations? Sure can. And let's go ahead and do that. We get x minus x naught divided by t. We're going to set that equal to V naught plus V divided by 2. Okay. Now, if we want, we could write delta x on the left-hand side divided by t equals V naught plus. Now, in the final equation that we are seeking, which is this over here, number 2, you will see that we do not have V. We have V naught. So this V over here, we're going to write this in terms of V naught. How? Substitute V as V naught plus AT as per this equation number 1. Let's go ahead and do that. I'm going to use blue color for this. V gets written as V naught plus AT divided by, the whole thing is divided by 2. All right. What does this give us? This gives us, we get right hand side equals 2 V naught. This V naught plus V naught is 2 V naught plus AT divided by 2. All right, so what's our equation now? Our equation now is delta x over t equals 2 V naught plus AT, okay, divided by 2, okay. And the right-hand side can be written as 2v naught divided by t plus at divided by 2. Now we want to get this delta x on the left-hand side. In the equation that we just got, it does have delta x on the left-hand side, but it also has this t in the denominator. That we do not want. So go ahead and multiply this equation by t. When you do so, this t that you're multiplying with, it cancels out t in the denominator of the left-hand side. What are you left with? You're left with only delta x. So here's your delta x. On the right-hand side, we have 2v naught divided by 2. 2's cancel out. We're left with v naught times this t plus 1/2 coming from this 2 times a times this t gives you what? T squared. So here you go. You got your equation 2. Delta x equals v naught t plus 1/2 a t squared. We got it. We got our equation 1 here. And we got our equation 2 here. Now what we're going to do is we're going to move on to equation number 3, which is v squared equals v naught squared plus 2a delta x. We want to derive this equation. How? Using algebra. Let's go ahead and write down our equation 1 and 2 for just in case. And the second one was delta x equals v naught t plus 1/2 a t squared. Now look at equation 3. It has v naught, 2 and delta x. And equation 1 and 2, they have all of these variables. In addition, it has t. So how about, oops, my pen's a bit miscalibrated. That's why it writes off. This t, how about if we get rid of these two t's from equation 1 and 2? In that case, can we get equation 3? Sure can. Let's see how. So equation number 1, we're going to rewrite this to solve for t. And that's going to give us v minus v naught divided by a. If for some, I hope you can solve this much by yourself, but if you can't, that's all right. Just let me know in the comments and I'll do it for you, okay? So what we're going to do is, here we have solved for time t. We're going to substitute it over here for this t and for this t. Where? In equation number 2. So that makes equation 2 equal to delta x equals v naught. Let's use yellow color to write for t plus 1/2 a, and t is v minus v naught divided by a, and it's going to be squared. Okie dokie. What does this give us? This gives us blue parentheses begin v naught v minus v naught squared divided by a. Blue parentheses close plus green parentheses begin, and we have 1/2 a and v minus v naught whole squared. That gives you v squared plus v naught squared minus 2v naught divided by a squared. Green parentheses close. Now you will see that inside the green parentheses, one of the a's at the top cancels out one of the a's at the bottom. Okay. And on the left-hand side, I have delta x. While in the equation that I want to solve for, that I'm trying to derive, has what? It has 2a delta x. And this equation has just delta x. How about I multiply this equation, the equation that I now have, the latest equation, the most recent equation, with 2a. And by doing so, I get 2a delta x together in one term. And that's what we want in our final equation. So we get 2a delta x equals 2a, blue parentheses, they have v naught, v minus v naught squared divided by a, blue parentheses close, plus, again we have 2a, green parentheses, we have 1/2 v squared plus v naught squared minus 2v v naught divided by a. Green parentheses, close. What do we have now? We have this 2 cancels out 2 in the second term in green parentheses and also does the a. Not just that, even in the term in blue parentheses, the a cancels out. So what do we have? We have 2 times v naught v minus 2 v naught squared. Let's put this blue parentheses around it. Plus, we have green parentheses inside which will have what? V squared plus v naught squared minus 2v v naught. All right. Now watch this. This 2v v naught and minus this 2v v naught, they cancel each other out. Let's go ahead and cancel them out. Here we go. Then we have this v naught squared minus 2v naught squared. These two give us what? Minus v naught squared. So we get minus v naught squared. And we have this v squared. On the left hand side, we have 2a delta x. Now this is basically your equation number 3, right over here. If you want, you could leave it as it is, or if you wish, you could add v naught squared to both sides. So what do you get? You get v squared equals what? Equals this thing, which is v naught squared plus 2a delta x. And here you go. This is your equation number 3 derived algebraically. So, seems like a bit of work here. This is all. Seems like quite a bit of work, but it really isn't once you get it inside your head, once you understand how it is done and what's the logic behind every step. Things are not that hard. Things are going to get hard though. So far they're not hard. All right. So this was our algebraic derivation of the 3 equations of motion. Next, what we're going to do is we're going to derive these same 3 equations using calculus. Let's hop onto that. Now we're going to derive the 3 equations of motion using calculus. Just like before, we are deriving these equations from the first principles, from the very fundamental equations. So which are the fundamental equations of motion in calculus? Those equations are equation of instantaneous velocity, v. It is equal to the differentiation of the position function with respect to time. This is your instantaneous velocity. And then we have a, the acceleration, instantaneous acceleration defined as the derivative of the velocity function with respect to time. Using these 2 equations, what do we want to derive? We want to derive the first equation, which is v equals v naught plus at. Now the question is, which of these 2 equations, instantaneous velocity, call it A, or instantaneous acceleration, call equation B, which of these 2 equations we're going to use to derive equation 1? Now look at equation 1. We have v equals v naught plus at. How about subtract v naught from both sides of equation 1? When you do so, you get v minus v naught equals at. And v minus v naught, this is change in velocity during time t. And in physics, we represent change by what? We represent change by a delta. So this is delta v equals AT, correct? Now this is basically delta V divided by T equal to A. And to be technically correct, we have delta T at the bottom. And in the limit that delta T approaches 0, delta V over delta T, it changes to dV over dt. So it makes sense to use equation B to derive V equals V naught plus AT. Let's see how. So we're beginning with A equals dV over dt. Go ahead and multiply both sides of this equation by dt. That will give you A dt equals dV. Now go ahead and take the integration on both sides. Here on the left hand side, A is a constant. Since A is a constant, it can be pulled out of the integration sign. What do we get? We get A integral of dt, and on the right hand side we have integral of dV. Question is, are these integrals on the left side and right side, are these definite integrals or indefinite integrals? These are definite integrals. Integral of dt, here time changes from 0 to final time t. And for velocity, it's going from initial velocity v naught to final velocity v. Okay, what do we get next? We get A, the acceleration, and the integral of dt, that gives us t, where t's value is going from 0 to t. And integral of dv, that gives us v, where the value of v changes from v naught to final velocity v. What does this give us? This gives us A times this t, this is a variable. Its value is going to be equal to the upper value, the top limit t, minus the lower limit 0, equals what? V's first value will be the top limit v, final velocity, minus lower limit v naught. Okay, this is AT equals v minus v naught. Go ahead and add what? V naught to both sides. What do you get when you do so? V naught plus AT equals V, which is V equals V naught plus AT, and this is nothing but your first equation of motion. This is nothing but your first equation of motion. Here, we got it. Now the second equation of motion, what does that say? Second equation of motion is delta x equals v naught t plus 1/2 at squared. Back to our fundamental equations. They are velocity equals dx over dt. This is our instantaneous velocity, and instantaneous acceleration is dv over dt. Now in the equation that we want to derive, what do we have? We have delta x, which can be written as x minus x naught. It is our displacement. And if you remember, the formula for average velocity is delta x over delta t. And in this equation, if we take the limit where delta t is going to 0, what does this equation change to? It changes to dx over dt, which is this equation over here. So you see that delta x, it is related to dx, and dx is contained in this equation for instantaneous velocity. So what we're going to do is we are going to try using this equation for instantaneous velocity to derive the second equation of motion. Let's see what we can do using equation v equals dx over dt. Just like before, we're going to multiply both sides of this equation by dt, and when we do so, we get dx equals v dt. I have also already swapped left hand side and right hand side. And on the left hand side, dx, position is going from x naught to x. On the right hand side, this v, it is not a constant, but it is a function of time. So what we're going to do is, instead of v, we're going to write v equals v naught plus at. The first equation, we get v naught plus at Then we have this dt, and we are going to integrate it. The limits of integration for dt are time t equal to 0 to final time t. Okay, let's go ahead and do this integration now. On the left hand side, we have x naught to x of dx. On the right hand side, I have t equals 0 to t of v naught dt plus t equals 0 to t of at dt. Good so far? Left hand side gives us x, that is the integration of dx. It's going from x naught to x. On the right hand side, the first term, this v naught is it's a constant. So pull this out of the integral sign and you're left with dt going from 0 to t. T is going from 0 to t plus acceleration a. It is a constant as well. Pull it out of the integral sign and inside the integral I have t dt time t is going from 0 to t. Very good. Now on the left hand side we get x, value of this x to be top value, upper value x minus the lower value x naught equals what? Equals v naught and then we have t where t goes from 0 to t plus we have acceleration a and then we are doing the integral of t, this t over here, which gives us t squared divided by 2 and the limits are 0 to t. What do we get now? We get v naught times t's value is first t, this top limit, upper limit, minus 0, the lower limit, plus acceleration a times, alright, how about pull this 2 out, it's a constant. Then t's value is the upper limit, t squared, minus 0 squared is just 0. What do we get? X minus x naught. How about we write this as delta x? We get delta x equals v naught times t. V naught times 0 is just 0 plus 1/2 a. 1/2 a times t squared. Here you go, your second equation of motion already derived. So now we have two equations of motion. The second equation, and what was the first equation? V equals v naught plus at. Third equation, what does the third equation say? Third equation says v squared equals v naught squared plus 2a delta x. Let's look at our first equations. Let's look at our fundamental equations one more time. Our fundamental equations are v equals dx over dt and a equals dv over dt. Okay. Which of these two equations shall we use to solve for third equation? These equations are what? A and B. Now we know that in our third equation we have acceleration and B has acceleration. In B we have velocity and here we have velocity. But equation B also has time t. That's not there in equation 3. However, equation 3 has v and delta x and equation A has v and delta x. So using A and B, if we could mutually eliminate dt and combine A and B, then maybe we'll end up with equation 3. We're going to do that and see what we get. We know that equation B is A equals dv over dt. Here we are going to use a little trick. We're going to use chain rule. We're going to say that dv over dt, this can be written as dv over dx times dx over dt. What does this give us? This gives us dv over dx and dx over dt. We know that this is equal to what? This is equal to v. So what do we have now? we now have an equation a equals dv over dx times this v. How about bring it in front? Now we are going to rearrange this equation. We are going to multiply both sides of this equation by dx. When we do so, we get a dx equals v dv. Now we can go ahead and integrate this equation on both sides. On the left hand side, this a is a constant. So basically all we are doing is taking the integral of dx. And on the right hand side, I have v and dv. So on the right hand side, we are integrating v with respect to dv. V goes from v naught, the initial velocity, to final velocity v. And on the left hand side, x goes from initial position x naught to final position x. Let's go ahead and pull this a out of the integral sign. What do we get? We get a x naught to x of dx. And on the right hand side, we get integral of v with respect to dv is v squared over 2. And v changes from v naught to v. Okay. On the left hand side, what do we have? We have a, and then we have x. That's the integral of dx. X goes from x naught to x. And on the right hand side, this v is first going to assume this value v, top value, top limit, v squared over 2 minus. Now this v, which v? This v is going to become v naught. v naught squared over 2. What do we get? A times this x here is first going to assume the top limit minus the bottom limit. What do we get? X minus x naught equals v squared minus v naught squared divided by 2. This gives us a times delta x equals v squared minus v naught squared over 2. Now we're going to go ahead and multiply this entire equation by 2. That gives us 2a delta x equals v squared minus v naught squared, which can be further written as v squared minus v naught squared equals 2a delta x. Go ahead and add v naught squared to this equation, and that gives us v squared equals v naught squared plus 2a delta x. Here's your third equation of motion derived using calculus. Now we are going to derive these three equations using what? Graphs. Let's get to that. Finally, the graphical method to derive three equations of motion. What kind of graph are we going to use? It turns out that we are going to use same graph, which is velocity time graph, to derive all the three equations of motion. So here we got our velocity time graph, where velocity is along the y-axis and time along the x-axis. We know that the slope of this graph, slope of VT graph, what does this give us? That gives us the acceleration. Okay. Now, let's look at this plot for a minute. In this plot, the object, it is starting at this point C over here. And its velocity is increasing along this pink line until it reaches the final point F. So the object's initial velocity is here at point C. Initial velocity is v naught. And the final velocity is at point E. Final velocity is v. Okay. Now, geometrically, the slope of this graph is equal to what? That is going to be equal to the rise, which is Fd, divided by the run. And the run is what? That is Cd. We're going to write Fd equal to Fb minus dB. And Cd is the time t. Time t during which the velocity changes from v naught to v. So Cd, instead of Cd, go ahead and write t. Now instead of FB, we're going to write V, and instead of dB, we're going to write V naught. V minus V naught divided by T. And we already said that the slope is equal to acceleration. So here we go. We have A equals V minus V naught over T, just like we have been getting. From here, we know what to do. Multiply both sides by T, and you get AT equals V minus V naught. Now go ahead and what do? You add V naught to both the sides, and you get V equals V naught plus AT. And that is nothing but our first equation of motion, already derived. Now to get the second equation of motion. Okay. What's the second equation of motion? That says delta x equals V naught t plus 1/2 AT squared. Now let's look at the same graph again. In this graph, we know that the slope gives us acceleration. In this graph, we also have the initial velocity V naught. The time t is also here. The only thing that's not here in this graph is delta x. But could we somehow get delta x from this graph? Sure can. How? We have velocity time graph. What is the area under the velocity time graph? The area under the velocity time graph gives you displacement, change in position. And that is exactly what we're going to do. We're going to use the fact that the area under curve, area under the curve of VT graph is what? That is equal to delta x, the displacement. Okay, so let's go ahead and put the graph over here again. Let me put it here. Here we go. So what we basically want is the area under the curve. And how do you define the area under the curve? That is the area between the curve and the time axis or the horizontal axis. That is going to be this area over here. Now this area, as you can see, it can be divided into two parts. It can be divided into area of this triangle, which is CDF, and the area of the rectangle. Which rectangle? ABDC. That's exactly what we're going to do. The area under the curve, we're going to divide it into two pieces. Area of triangle. Which triangle? CDF plus of rectangle. What rectangle? ABDC. Okay. Area of the triangle CDF. That is going to be 1/2 times the base. Base is CD times the height. And the height is DF. Okay. That is one piece plus the area of the rectangle. Area of the rectangle ABDC is going to be the product of the two sides, which are AB times DB. Okie dokie. Now here 1/2 remains 1/2. CD is time t. Now DF, let's just leave it here for a second and we'll get back to it. I'm going to write DF as just DF for now. Okay. Let's move on. AB. What is AB equal to here? AB is equal to time t. Okay. Time t times dB. What is dB? dB is V naught. So here we go. V naught. What do we have now? We have V naught times t is, just write it as V naught t plus 1/2. And then from this equation over here, we have 1/2 times t times df. Let's compare this equation with the right hand side of delta x. And when we do that, we see that V naught t equals V naught t. So that means 1/2 t df should be equal to 1/2 at squared. That means df should be equal to at. Now how do we make df equal to at? Very easy. How? The slope of CF, slope of the line CF. What is that equal to? The acceleration, that's the slope, and it's going to be equal to FD over CD. From here, FD equals CD times A, but CD is equal to time t. So FD is equal to AT, or DF is equal to AT. Let's go ahead and substitute this DF here as AT. What do we get? We get 1/2 times t times AT plus V naught t equals 1/2 AT squared plus V naught t. What is this equal to? This is equal to the area here, this area over here. And what is this area equal to? This area is equal to displacement delta x. Why? Because this is the area under the curve of velocity time graph. So what we have done is we have essentially already solved or derived that delta x equals what? Delta x is equal to V naught t plus 1/2 AT squared. And that's what we had set out to derive. Here we go. Already derived using area under the curve of velocity time graph. Moving on to our third equation. Third equation says v squared equals V naught squared plus 2a delta x. We're going to use the same graph again. What's that graph? Here we go. This is the graph. Now you can see that this equation has delta x. Where does delta x come from? Delta x comes from the area under curve of velocity time graph. So here we have to find the area under the curve of velocity time graph again. V naught is here. That is equal to AC or equal to BD. We have acceleration A here in the equation, and the slope of straight line CF represents the acceleration. And this final velocity V, we have that as well. The magnitude of the height AE, that is equal to V. Let's see. We want to find the area of this shape. What kind of shape is this? It's a trapezoid. So area under the curve equals what? That equals delta x. And area under the curve is going to be what? That's going to be area of the trapezoid. What kind of trapezoid is it? ABFC. All right, ABFC. Now the formula for the area of the trapezoid is 1/2 times the sum of the two parallel bases, which are going to be AC plus BF, times the perpendicular distance between the two parallel bases, which is AB. Okay. This is equal to 1/2 times AC. AC equals V naught, and BF equals V. And AB is equal to time t. Now here's the thing. In the equation that we're trying to solve for does not have t. That means we do not want this t over here. How do we get rid of this t? We know that the slope of the line CF, that equals the acceleration of the motion. So here we go, the slope equals the acceleration, and slope equals FD divided by CD. Now we know that FD equals FB minus DB, which is V minus V naught divided by CD, which is time. So we have here A equals V minus V naught over T. Well, this is basically how we derived our first equation. We can write this as T equal to V minus V naught divided by A. We're going to substitute this value of time. Where? For this T over here. Let's go ahead and do that and see what we get. So we have delta x equals 1/2 V naught plus V. And time T is equal to what? V minus V naught divided by A. All right. Now we have delta x equals 1/2, this in the denominator, V naught plus V times V minus V naught. 1/2 A V plus V naught times V minus V naught. What do we get over here? A plus B times A minus B is A squared minus B squared. V plus V naught times V minus V naught equals V squared minus V naught squared. Times we have 1/2 A equals delta x. Now from here it is easy. All you have to do is multiply this by 2A on both sides. What do you get? 2A delta x equals V squared minus V naught squared. Rearrange this and you get V squared equals V naught squared plus 2A delta x. So here we go. We have derived all the three equations of motion. What kind of motion? One-dimensional uniformly accelerated motion using algebra, using calculus, and graph. And next time, in the next lecture, we're going to talk about motion graphs. All kinds of motion graphs and their subtleties, and we're going to have a lot of fun working on them. Until then, have a good one. Bye-bye.